Hi, I'm an old guy and I do maths. What does the function of x to the power of 5 look like when we graph it? Let's go to work. So let's set up our Cartesian plane here, rough as it is. Now, how we're going to resolve this is by simple arithmetic and doing what the function tells us to do. But there are a couple of preliminary observations. This is an uneven power, and in general, uneven powers that look like this, x to the 3, x to the 5, x to the 7, even x to the 1, occupy, for the main part, this quadrant here and this quadrant here, and they run in their positive form, bottom left to top right. So that's what we should expect from this, because it is an uneven power. So it has both negative and positive values of y. Okay, well, let's start with a little bit of substitution. We'll put 0 into this, and 0 to the power of 5 is 0. And that worked well, so what we're going to do is we're going to do the same thing with some different numbers. 1 to the power of 5 is 1. If we use negative 1 over here, negative 1 to the power of 5 is negative 1. It is not to be confused with what I'm about to write here. Now, the thing is that this will get you the same result. But this is actually what it is. And it doesn't matter a huge amount in this case. But let's say we had a positive power here and a positive power here. We'd get different outcomes. So just be aware of that. This is what we're discussing. It is negative 1 to the power of 1, 2, 3, 4, 5. It is negative 1 times itself 5 times. And so that gives us a result down here at negative 1. So we already know that this thing passes through the origin, and it looks suspiciously like we might have a bit of symmetry going on. Let's try 2. 2 to the power of 5 is 2, 4, 8, 16, 32. And I'm drawing this wildly out of scale. So just be warned about that. So that is 232. And the corresponding points down here are negative 2, negative 32. Let's try 3. So we'll put that up here, and again you're going to see the deficiencies in my scale. 3 to the power of 5 is 3, 9, 27, 81, 243. 3, 243. Okay, let's put the corresponding point down there. And what we get is something that those of you who've seen cubics will go, I know that shape. I know roughly what this thing looks like. Now, how does this distinguish itself from a cubic, which is not really the purpose of this video, but I'll just do it quickly here. So let's put in x to the power of 3 here. So that is x to the power of 3. Now, what you can't see because of my poor scaling here is that this has a much flatter area around here than this. So, two things occur. This is much flatter, and because we've raised this to the power of 5 rather than the power of 3, the y values go streaking off in the positive and negative direction of the y-axis far more so than they do here. So what you wind up with is a shape like this, approximately. You've got a flatter area here, and much greater y values once you move out to about 2. So now that's an approximation. If you want to get a really good look at this, get a graphing app and have a look at the difference. What you'll learn is that if this is raised to the power of 7, this becomes even more exaggerated. It's flatter along here and then takes off again up and down the y-axis. Anyway, I hope that you found this useful. What's the simple way of dealing with this? Just substituting in some numbers and seeing what you get. Joining the dots. Couldn't be simpler. Thank you very much for watching. I hope that if you did find this useful, you'll like and subscribe. See you next time. Bye.